Hello, lovely humans! Jen Foxbot here. In this episode of Machine Learning Math Mondays, we are going to start to look at the things that we need to learn to actually be able to apply machine learning to real-world problems. Yay! First up, feature scaling. Woohoo! What is it and why should we care? Well, feature scaling has to do with changing the range of the features of our data set. And by feature, I really just mean the different types of data that go in to our machine learning program. So for example, if we're looking at weather, we might want to think about temperature and rainfall. We should care because we want to minimize our cost function as quickly as possible. We're using computer resources, which contributes to climate change, and also we don't have all the time in the world, so let's get it as fast as possible. Feature scaling helps us do that. Okay, so the ultimate goal of feature scaling is to get our features into equivalent ranges. So for example, a helpful range to keep in mind is that we want to map our features, xi, ideally to something like -1 and 1. It doesn't have to be exactly this range. If you have something like -2 for your first variable and 5 for your second, and something like 0 to 1 for your second variable, this is fine. We'll do a blue check mark. Yeah, okay. So, and then if you have something like -100 for your first variable, this is x1 and x2, to 100, and something that's a lot smaller, like 0.1 for your second variable, negative, to positive 0.1. This is what we want to avoid, because in this case, our first feature has a possible range of 200, where this has a range of 0.2. So this doesn't work very well. And what ultimately happens is you get these parameter plots. So in this case, let's start with this one. In this case, if you plotted x1 and x2, you would get something that's like a smushed circle. Like if you took a pancake and squished it, or an orange. But with this one, if you have a contour plot of these two, you get more of a bullseye. And this is what we want because it's way faster to minimize our cost function. Keep in mind that these are j of theta contour plots. Okay, so feature scaling helps us to get to the point faster. All right, so how do we actually do it? We are going to use a technique called mean normalization. And I'm going to look at my notes to make sure that I get this right. So what we want to do is replace each feature from our original data set with a scaled version. So we're going to replace the original feature with xi minus ui, where this is some scaled version. Or, well, I should just say this is some scale factor, which we'll figure out in a sec. So the goal is that our features have effectively 0 mean. It's not that our data is kind. Well, I hope that our data is kind. But basically, like if you were to find the average of this new feature, it would be 0. Like we were saying, if our feature is on a scale of -1 to 1, it'll effectively have a 0 mean. So that is the goal here. So how do we actually do that? Well, let's look at an example of predicting the weather, because critical, right? Yeah. So let's say that our first feature is temperature, And so that is going to be on a range from, let's say, negative 100 Fahrenheit to 100 degrees Fahrenheit, because I'm in Seattle and it very rarely goes above 100. So we are going to scale this by using an equation where we have the temperature of interest. So I'm just going to write temp for temperature. We have minus the average temperature divided by the range of temperatures. And so this would be the temperature of interest minus, I'm going to use 55 for the average temperature in Seattle. And our range is going to be 200. And then let's say our second feature, x2, is going to be rainfall. And this is going to be on a scale from 0 to 5 inches. And so this is going to be rain in inches minus average rainfall divided by range. I should say temp range and rainfall range, as specific as possible. So then this is going to equal rainfall minus the average rainfall in Seattle is actually pretty low. So I'm going to use a value of 0.5 inches. By the way, I made this up based on my personal experience of living in Seattle. I did actually look up these ranges, so these are reasonable. And our range in this case is 5 inches. Yeah, fun fact, the most it's ever rained in Seattle is just over 5 inches, so we're not that rainy, it just rains a lot. Okay, which maybe means that we would want to have another feature to capture, what days is it most likely to rain. But anyway, we're going to keep our model simple for now. So basically, we would take each data point that we have and apply these equations and then get out our scaled version. So the goal really, or I guess I should say, if I generalize this, the goal is to be able to apply this to any data set, right? So in general, we're going to have xi equal to the original xi minus this scale factor, which is the average divided by s. Actually, let's put subscripts here so that we can be very clear. Well, actually, okay, we'll say xi. Xi is fine. This is my thought process as we're going. I hope that is actually helpful. So, and then this is going to be the range. Like min to max. Or you can also use the standard deviation, which I'm going to abbreviate STDev for standard deviation. So you have some options here, but this is the general equation for scaling features. Yay! Okay, so we're going to end by doing an example. Let's say we have let's say we have x1. We're looking at a particular day in the year where it was, 40 degrees Fahrenheit. Woo, little door thing. And let's say it rained 2 inches that day. Actually, I'll actually write inches so you can see it. So now we take the feature and we plug it into that equation. So we have 40 degrees Fahrenheit minus 55 degrees Fahrenheit divided by 200 degrees Fahrenheit. And this is going to equal 40 minus 55 is negative 15 divided by, actually, you know what, I'm going to change this to make my math a little easier. Okay. So this is the sneaky part about doing demonstrative purposes. I can change my data because my data is made up. Okay, so 45 minus 55 is negative 10 divided by 200. The units cancel. So we end up with negative 1 over 20. And for the rainfall, we get 2 inches. We'll go down a little bit to have some space on the board. 2 inches minus 0.5 inches divided by 5 inches. Ooh, I'm going to do the same thing here to make my math easier. Look at me. Okay, 2.5 inches. 2.5 inches. Oh, this is why I love teaching. I can change things on a whim. And my justification is that it makes math easier to do in my head because I don't feel like getting out a calculator. Okay. So 2.5 minus 0.5 is 2 divided by 5. And again, this is the units cancel, so unitless. All right, so our first feature scaled to negative 120, and our second feature scaled to 2 out of 5. And so what we would do is we would go and plug that back into a new array. Remember, don't write over your data. Just when you're coding, save it into a new array. So we'd have like x1 scale or something like that. And this would go to x2 scaled. And this would help us be able to minimize the cost function or finish gradient descent way faster. Yay! Okay, so I hope that that is helpful. You can use machine learning to do things like predict the weather, but our predictions are only as good as our data. So, and gathering accurate data is really, really difficult. So it's always important to keep in mind that technology is really useful, but it does have its limitations. Not a magic wand yet. Okay, so please let me know if you have any questions about feature scaling. If you enjoy these videos, feel free to share with your friends, subscribe, like, all that good stuff. It makes me really happy because more people get to see my videos, and it motivates me to keep going. Okay, thank you very much for watching and for spending some time with me. I'll see you next time. Bye!